Hello, everyone. My name is Davide Schaumann. I'm an assistant professor in the Faculty of Architecture and Town Planning at the Technion in Israel. The title of my talk is Toward Convergent Human Building Adaptability. I have a background in architecture, but also in computer science and entrepreneurship, and I'm currently an assistant professor at Technion, where I created the Intelligent Place Lab. So built environments are designed to host a wide variety of activities. But built environments are fundamentally static, and human activities are dynamic, and the needs of the people continuously change and evolve. This is an example of a design hospital in Israel, and this is an example of how the building is used. This is in 2016, well before COVID. So you can see that there is a mismatch between the design and the way the building is used. This is not only pertinent to hospital, in office spaces, for example, COVID created a fast transition towards work from everywhere. So it creates major occupancy fluctuation in offices, which are heavily underutilized at the moment. Extreme climate change events are also impacting buildings by creating operational disruptions, for example, in transportation facilities, such as airports. So the question I ask is, how can we design environments that meet ever-changing people's needs? Building information modeling is the go-to standard in representation in the architectural world. You have an integrated representation, which encompasses all the physical aspect of the building, but it is not representing the human in the building, the occupants. So what I advocate as a solution is to model not only the spaces, but also the people, the occupants, and the activities they do. Each one of these modeling domains come from a different world of architecture, social science, and operational research, okay, and industrial engineering. So these worlds need to be combined to have an integrated representation of human behavior in built environments using a multi-agent system where each agent is able to interact with other agents and within a virtual environments to carry out their goals. So agents are participating narratives according to their roles. Their narratives is a sequence of events that basically occur in a building, which represent their use scenarios. So these narratives can be simulated in a virtual world. For example, this is a hospital facility. You can see here that on the bottom right, you have doctor and nurses doing a scheduled patient check round, but also visitors may come in at random times. And you see here visitors coming in, but when the medical staffs come in, the visitor needs to leave. So there are a lot of social situation and interaction which are accounted for in this simulation. Multi-agent simulation can also be coupled with other simulations, such as thermal simulation. So here you have a simulation of the heat, let's say, in the building caused by the heat that the body generates. So you have a simulation of heat, a simulation of comfort of the occupants, and if the heat surpasses a limit, the occupants may decide to change their behavior, such as leave a room or turn on the HVAC system. So this is called the co-simulation because you have a simulation of temperature, decision-making, comfort, and even the movement of people in the buildings. So these type of tools can help optimize the building design. So at the design stage, architects can analyze walking path and distances, environmental parameters, spatial congestion, social interaction, etc. And they can also compare design options. They can say, for example, in the bottom option, there is a day room for social interaction, which is not present in the upper option. So you can simulate the differences and see how this affects the behavior of the occupants. So far, you're focused on optimizing the building design. So artificial intelligence is used to model synthetic agents that simulate the behavior of real agents. But these AI tools can also be incorporated into the building itself so that we can optimize building operation after a building is designed and in use. So in this case, on the left-hand side, we have smart humans that make decisions at the design phase. And on the right-hand side, we have smart buildings that optimize the operation of buildings. This is a paradigm shift in the field because buildings are becoming intelligent. They're able to sense, reason, act, and interact and adapt dynamically to the needs of the occupants. So what buildings can do? They can, for example, simulate a different allocation of resources, such as buildings spaces, and optimize the way buildings are currently used so that you can optimize environmental factors, but also comfort and operational efficiency. This is a scenario where the building simulates future resource allocation scenarios. This is a sequential decision-making process because the moment you allocate resources in a position, you may create further conflicts down the future. So you need to simulate all kinds of options and basically up into the future, into far future, to see if they do not create conflicts. This is an optimal, for example, resource allocation strategy, but it's just an example because in reality, the building needs to simulate hundreds of thousands of options. This is a very complicated process. So what I advocate in order to get towards human building convergence is to merge an approach of optimized building design made by smart humans to an optimized of building operation enabled by smart buildings. So in order to do so, we need three things: create artificial intelligence system to inform decision-making, integrated facility design and operation, and convergent goal of improving social and environmental sustainability. Thank you very much for listening.